Hi there, and welcome back to Triplicate, and we have not had a look at the big rig, the remote control lorry, for a while. So I thought we'd have a look at it today. So where have we got to this? Originally, the idea was, well, as it came, it just had left, centre, right on the steering, and full speed forward, full speed reverse, and off on the direction. And the idea was to put the Arduino between the remote control input and the actual motors and improve it, make it drive better, more like a sort of scale version of the real thing. But we've already concluded that we couldn't get the steering to work as we wanted, so we replaced that with a servo, and we've concluded that we can't get it to drive how we want it with the existing motor setup. Basically sort of scale speed, top speed on the road 100, so scale speed about 3 miles an hour, and to manoeuvre we actually want to go about that sort of speed on the road. You can tell with it, it just jerk, jerk, jerk as I'm trying to push it. So we have decided, yet more mission creep, that this motor that's driving the back wheels, or one pair of back wheels, needs to be replaced. Now the problem was not getting it to go as fast as we wanted. It does that as it is. The problem was getting it to go slowly. So I cast my mind back to the cat food feeder project, one of the first ones we did, and that went round once in 50 hours, so that's slower than we need. And that used a stepper motor, so should we try a stepper motor? Now I bought a number of motors to try out, which is probably all we'll do in this video. So I have a couple of stepper motors. That one, which is way too big, and use those in excuse me, professional 3D printers. And that little baby one, which I believe they use in the focus mechanisms of cameras, which I think is probably going to be too small. Anyway, we're going to try and make them go round and evaluate them. I also bought this, which is just a brushless DC motor, which is probably going to be too fast for our application. But we're going to give it a try anyway. And I bought that, which is a brush DC motor with a gearbox, but a lot higher quality than the one that's came with the big green. So just for comparison, we're going to try that as well. Now bought a motor driver board with the stepper motors, also which will be controlled by the trusty Arduino, and this thing, because it spins fast, needs a specialist driver board, so I'm going to try that. Bought one of them to try, and this we might just run from a power supply, see how it goes. And I think first up, because we don't need to do any coding or anything, we're going to try this guy, which has 4 wires coming out of it, 3 phases and a common, and so over this driver board, which has common and W, V and U, and takes 5 to 12 volts. So I will find out what the connections are to this motor, and wire it up. Okay, so set up somewhat precariously. Managed to find the wiring for the motor and the board. You have clockwise and counterclockwise, off and on, 2 jumpers, speed here, power here, which is 5 to 12 volts, 5 volts currently, and with the current turned right down so we don't fry anything. So I turn the current up and it comes up to 5 volts. So what happens if I turn up? The little light comes on, that's always a good sign. What happens if I turn the speed up? Oh. Right, it's bouncing off the current limit. Oh. Well, something's happening. No, it kicks and revs and stops. What happens if we turn her up? Okay, it spins. Ah. Right, I think we need to secure it better. Okay, I will do that and bring you back. Okay, I've got a piece of bent plastic, attached it to hot melt glued onto the plastic. The shaft going through a hole because I didn't have any screws that were 1.5mm or whatever they are. So, shall we try again? Should be good to go at that. So let's turn the speed up gradually, and it starts a bit and stops. Right, I know what I am going to do. There we go. Should be able to see it going now. Right. Ooh. So this board has 2 chips on, neither of which I've looked into. So it's obviously got some intelligent drive somewhere which is doing something less than intelligent. Right, well, we'll turn it up gradually. So that's increasing in speed. Hopefully the whizzing noise from the motor is coming through on the camera audio. Some kind of thermal cutout or something. No idea whether this board and this motor are compatible, so it's possibly not totally unsurprising if it's not working 100% as you'd hope. Okay, well it does say 5 to 12 volts, so what I am going to do is turn the voltage up do 10 odd volts, which is what we would be using in that, and we'll try that again. Yep, it's unfortunately not too stable at low speeds, which is our problem. And again, and it stops up there. I suspect that the motor is probably lower impedance than the chip is supposed to drive, hence it's shutting itself down due to overloading. So now what I'm going to do, because I'm new to these brushless motors, I am going to take the picoscope and we're going to have a look at what's actually being fed into the motor. And I'm also going to rig up my little light sensor so we can actually see how fast it's going round. Okay, so here we are. I have, apologies for the hand cam, so this is the reflective opto sensor that we were going to use to measure the back wheel speed of the truck, which is just clamped to my plastic bracket, and here the pen didn't work, so I've stuck some copper tape on. This is the most reflective sticky back thing I have. And that goes out to the scope probe, and this is all powered from 5 volts on the power supply, and this scope probe goes to one of the outputs to the motor. So shall we see what it does? Okay, so we can, on the picoscope, the blue trace at the top is the reflective piece of tape. Should we see if we can get it to... So if I wind the motor slowly across there, yeah, up she goes as the tape passes, and back down she goes. And the red trace is, as I said, one of the inputs to the motor. So shall we come on. Okay, so we've got it to run at a steady frequency. We'll just go to there. So, as you can see on the bottom scope trace, there's a lot of PWM stuff happening there, which I guess is how the chip manages to drive it without cooking. And if I break that with my fingers, well, you can see to there. Ow, that's hot. Burnt fingers now. You can see the electronics compensates and runs around slower as the motor gets slower. And if we go to there, So there's one cycle, and as you can see it repeats in a pattern, and we get 1, 2, 3, 4, 5, 6 of these patterns per revolution. So I think we're going to leave this motor for now, because I suspect it's going to be a problem to drive and it's not going to run too well at low revs. So let's move on to a stepper motor. Okay, so here we are, set up to test the big chunky stepper motor. I've gone with that because it's just easier to work with something that's nice and big. So this is just a plastic disc with a piece of paper glued to the underside, and so there we have the reflective opto sensor again, and the disc has a rather ineptly drawn black stripe on it, which should give me a signal every time it passes the opto sensor. And here we have the Arduino, which is 6 output lines, so 2 windings, and for each it has output 1 high, output 2 high and enable, 2 pairs, and this wire goes off to power the motor. The actual chip is supplied from the Arduino. So I have stuck the disc to the motor shaft with a horrible great blob of hot melt glue, stop it sliding round. I've connected one scope probe to the optical sensor, and the other scope probe is in the blink light, the light on the Arduino board, which you're just using as a timing mark. So if we run that, there's no power to the motor drive at the minute, and as you can see it's not triggering off that channel, but that is just the built-in LED on the Arduino, which is just high the first phase and then low the rest, and you can see that's what it's doing. So if we put the motor on and bring the voltage up, so you can see it's chugging around rather slowly. So let's see if we can get it to go any faster. So this is the delay. It moves on to the next phase every delay. So should we half that, see what we get? There we go, going around twice as fast. So, well, we'll just keep going to see how fast we can make it go, shall we? So that's 22.5 times as fast. Okay, that's good. You can see that occasional dip as the mark comes round. Should we try 10? Yep, that's good. Shall we try 5? Okay, and you can see here it's detecting the optical sensors working, detecting the rotation. Should we speed her up some more? Let's try 2. Wrong one. Yeah, and that's working nicely, and that is 50 milliseconds a division. 1, 2, 3, 4, 5, 6, 7, 8, about 400 milliseconds, which is about 2.5 revolutions a second. Okay, I'm going to get it to go. One faster, so should we try that? Oh, doesn't like that. Doesn't like that. So we'll put it back to 2. So that would be fine. We want about 10 revolutions a second max, so we could gear that up by 4 and it'll certainly go slow enough. So that would work, except that is way too big to fit in the truck. So I guess it's time to try this one. Okay, so here it is in a little clamp to hold it in place. I'll attempt to zoom in. There you can see better. And 4 wires on those little pins, and that was a bit of a tricky job because it's all very small. And on the top we have just a cardboard disc held on with another great gob of hot melt glue, and the code and the wiring are the same as for the big stepper motor. I've just turned the current down some on the power supply. So shall we fire it up and see how it goes? Okay, so here we have the code, which is exactly the same. Set the delays back up to 100 milliseconds. So that's one complete step through the phases in 400 milliseconds. So should we fire it down and see what she does? Okay, it's bouncing about because there's no damping, and I'm just switching each phase on and off. You get smoother motion if you cross over, so you have one phase on, then both phase on, then the second phase on, etc. We're not doing that for now, and that is about 2 or 3 seconds. Right, I'll time it off the video rather than getting the light sensor out. Okay, let's see how fast it'll go. So 50. Hit it. Oh, it's whizzing around nicely. Okie dokie. 20. We try 20. There we go. Not sure that is 2.5 times 50. Gonna time it off the video. And shall we try 10? Nope. Go on, we'll put it back up to 30. So I think that one is going to be completely useless, because we'd have to gear it up and it's not the most powerful ever. You see. But fun to try. So what's next? Okay, so I said I'd have a look at this DC brushed motor with the metal gearbox. Just not higher quality than the one we were using, just for comparison. So shall we see what happens when we apply some voltage? I believe it's 6 volts. Right, a bit of proper investigation here. I am going to pinch my cardboard disc off the other stepper motor and mount it in a little clamp, and we'll get a better idea of how fast it's going round. Okay, here we are, cardboard disc pinched off the small stepper motor of a moment ago, held on with another ugly great blob of hot melt glue. So shall we see how fast it goes at various voltages? So shall we start? Right, try this time. Yay! So that's 6 volts. I'm hoping we can measure that off the camera. That's 5 volts. 4 volts. 3 volts. 2 volts. 1 volt, and should we turn it down very, very slowly and see at what point it bombs out. When that's less than half a volt. So around 200 millivolts, around 100, between 200 and 150 millivolts, it dies. Well, again, I shall try and measure the speeds off the video, and before we dismiss this little motor out of hand, shall we see what speeds it was actually turning at when it was going fast. Alright, and I can't leave the brushless motor It was a bit inconclusive. That board didn't seem to be driving it entirely properly, so I've glued it back down with some more hot melt glue, and let's see what it's actually doing. Now inside there are 9 coils going round in 3 sets of 3, I'm guessing, and this is basically a magnet. There's just a magnet round the inside of there. So if we wanted to drive it ourselves, what order would we connect these windings? Now the brown is the common, so let's just see where it finishes up, because if we statically, one of the magnets around here will align to one of the coils when we apply a DC current, like that. So what we're going to do is take a pen and mark yet another mark on here. So this is just to this side of this copper tape. So I am going to connect the black. So I am going to put a mark here and call that B plus. You see this ending up not being too legible. I'm then going to try the red. It's going to zip round that way. So that's R plus. I'm going to try a yellow, which has zipped round to here. Y plus. And round to here, and that's another B plus, and so on. And I will spare you me going all the way around. Okay, so now let's see what happens if we connect our 3 sets of coils the other way. So connecting the common to the positive, and let's zipper it around there somewhere. See where the black goes. Right, so that is in the middle. Black minus, so you're going to go around here. Red minus, yellow minus. Okay, so we have a cycle. Fine. Goes black plus yellow minus, red plus black minus, yellow plus red minus. And we have 6 of those going around, so that's 36 separate steps. So all we have to do is connect the common to the appropriate one of these 3 in the appropriate sense in order, and it should go round. So shall we try it? Okay, so to drive this, it has common, just the brown wire, and 3 inputs as we have just investigated. And to drive it, each one of these we need to be able to either connect to low, high or not connected. So unfortunately these things are in pairs, so you get 2 inputs, 2 outputs, and then for each of those 1 enable. So this is the one that was driving the motor in the big rig, which I've taken out again, and this was the new one we were using to investigate, and we're just using one side of each of these, so that's why it takes 2 boards. You see 1, 2, 3, 4. So first up, we'll try running it with just positive inputs to each phase. That is, the common is always connected to ground. So here's a bit of code. Again, we have a phase variable which just is 0, 1 or 2 in turn, and if it's 0, the black line, the black phase is positive, 1, the red phase is positive, and 2, the yellow phase is positive. So output 1 is the common, 2 is the black phase, 3 is the red phase, and 4 is the yellow phase. And 0 and 1 just flick the built-in LED so we can see it's doing something, and it's incrementing the phase on every 1 second. So shall we fire this down and see what happens? Okay, so the built-in LED is going, and at the moment there is no current drive. So if we bring the current drive up, we can see it goes round every second. Oh, what I should have done before, put the mark on there so you could see. Okay, so now we've got a mark on the top so you can see it going round better. Okay, that's good. Okay, so now let's add the negative phases in between. So we have black phase positive, yellow negative, red positive, black negative, yellow positive, red negative. So now there are 6. So shall we try that? Okay, as we come around here we can see that is stepping into these intermediate ones as well, so that as far as it goes is working nicely, but that's a bit slower than we want the motor to go round. So shall we try speeding it up? And here's the delay, so a factor of 10. Let's not muck around. Okay, that looks nice, and double it. Still good. Down to 20 milliseconds. That's the time between it changing the phase. So and there we go. You try down to 10. I mean, this thing claims to run at 14,000 RPM, so this is really crawling. Oh. So that's actually moving at a reasonable pace now, but okay, we'll go down to 5 milliseconds. So that one won't, no it won't start. I wonder if I, oh there we go. If I give it enough of a kick it'll start. Now when we had it on the pre-made board, when you started it off it would come up to accelerate up to speed, so I wonder if that's the problem. So I might now do something with the code and see if we can get it to accelerate up to speed and see how fast we can get it going that way. Okay, so in fact I didn't get any further with trying to run this one because the whole web-based Arduino editing and uploading system seemed to fail on me and just wouldn't work, so I've got to look into that. But for now I'm going to call it time on this video. So we've had an interesting play with some electric motors, and what have we learned? Which is the best one? Well, this would absolutely suit our purpose, except there's no way it's going to go in place of that one. Sadly, this little guy is too slow and too weak, which I thought it would be. Just interesting to play with, so whoop, we'll throw it on the floor. That'll do. This guy, I think I might have been missing a trick on running it, but then again it didn't run too well on the proprietary driver board I got. So I might get another brushless motor to have a play with and see how that goes. Similarly, I might try and get a stepper motor that'll fit in place of that one and give that a go. But the current best bet is back to DC brushed motor, but with the nice metal gearbox. And I might put that in and see what I can do, see if I can make the thing go slow enough with this motor on. It sort of wasn't far off. So I will do a bit more digging and make a decision, so then we can mount it and actually move on with what we're supposed to be doing, is getting this thing working how we want it. So I'm gonna call it a day for that. Like if you're interested in electric motors, subscribe would be nice, thumbs up would be nice, and for now it's goodbye from Triplicate, home of interesting electronics. Goodbye.